In work and energy approach, we discussed that there are certain situations where the Newton's second law applied directly becomes complicated. You can still use it, but it's much easier to use the work energy approach. So we talked about the work energy theorem and the condition under which it is applicable. Today we talk about another approach which again is coming from the Newton's second law, that's called the impulse momentum approach. So in fact, the Newton's law that we talk about all the time, the second law that was given by Newton, was given in this format. The text size okay for those at the back? So force acting on a particle, we are talking about a particle till now, is the time rate of change of the linear momentum of the particle. And you can see that it is the same as what we have discussed. F is equal to mass times acceleration. Now the thing is that this approach of force being the rate of change of linear momentum, although it's interchangeable with F equals ma, it becomes more generalizable when we talk about a system of multiple particles, or more generally a rigid body. So we will stick to this form of Newton's law rather than going for F equals ma later. We can now integrate this equation, call it equation 1. The left hand side is called impulse of force F or linear impulse. We can see the contrast here with the work energy theorem. So in work approach, we had F dot dr. So we are integrating the force along the path. So if you have F given as a function of your position, then finding impulse is complicated, because you have F as a function of position coordinate r or x, y, z, and you are trying to do F dt. Okay. So we do not know how the motion is happening in terms of r as a function of t. This approach can be used when you have F given as a function of time. How is force changing with time? in this form, it says that impulse will change linear momentum. So, the initial linear momentum, if you provide an impulse, will change. So, that gets added, the impulse gets added to the linear momentum, and you get the final linear momentum. If I was to write, this is a vector equation. If I was to show this vectorially, so I will draw initial linear momentum, then the impulse, integrate f times dt over the time from t initial to t final, and that gives us the final linear momentum. So, this diagrams are quite useful sometimes for visualization. So, this is called the impulse momentum diagram. Now, we classify forces as impulsive and non-impulsive forces. So, impulsive forces are large forces that act over a short period of time. We know that from collision. We have studied collision to a great depth in terms of problem solving. So, collision, typically what happens during collision is a large force acts on a body for a very short duration of time. So, these kind of forces are called impulsive forces. You can figure out what non-impulsive forces are. Now, let us look at the impulse momentum equation. That is the initial momentum plus the impulse equals final linear momentum. So, can we conclude that non-impulsive forces do not change linear momentum? No, right? I mean, no. That is because if you give them large enough time, they will change linear momentum. When take an object that you throw from a height, at this point it has no velocity, no momentum, but by the time it reaches the ground it has a momentum, and the impulse in this case is provided by mg. But during collision we used to neglect mg. The mg is a non-impulsive force. It does not act for a very short duration, and it does not have a very large magnitude as compared to something, of course, but usually impulsive forces are forces which act like impact or collision and so on. But that does not mean, do not confuse that if a non-impulsive force is the only force acting for a long duration of time, then you have to consider the impulse because of that. So, the idea of impulse for us is we always have Tf minus Ti as a very small time, but that need not be the case. You can also apply this for a large time. So, let us take a motivational example. So, we have a 1 kg ball that hits the floor at 1 meters per second. And then it rebounds with the same speed. The collision lasts for 1 millisecond. The question is, does the force of gravity play a role in momentum change during collision? Problems clear? So what I want you to do quickly is find out the impulse of the two forces in this case. One is the force because of the normal reaction during collision, and the other is because of mg, because these are the two forces acting on the ball during collision. We'll call it normal reaction from the ground and can we please calculate the impulse because of the two forces? You can assume that the normal reaction is uniform during collision, same value during impact, the complete duration of impact of 1 millisecond. What's the momentum change here? Final momentum is 1 meters per second. Let's say this is x and this is y. J hat, and initial momentum was downward, so -1. N is not known, but I said that you can assume it's a constant over the collision, so you can take it out of the integral, and so is mg. Mg is also constant, and then you have 0.001 second. So what we see is n minus mg is 2 divided by 10 to the minus 3, so that becomes 2000 newtons. This is unit. Mg is it's a 1 kg ball. You can take g equals approximate as 10 meters per second square. So we see n is 2010 newtons. You can see n is around it's 2010 newtons, and mg is only 10 newtons. a very small percentage, and that is the reason we usually neglect non-impulsive forces when doing the integral over short period. But if you were doing this over a long period, so the mg will be acting throughout the long time period, but this normal reaction will only act for a short period. So then you will have to consider both. So next is conservation of linear momentum. That is something I told you. You can assume that n is act as a uniform normal force during collision. That was an assumption, and we do that. We assume those things. That is not correct. That is not a correct assumption, because we sometimes model it as a spring. So during collision, it's a spring. We assume model it as a spring gets compressed and then expanded. Of course, spring, the force is proportional to displacement, the deformation. Okay, but we assume here, in this problem, we assume that F was uniform during collision. Okay, so let's move to linear momentum conservation. So there are situations where the impulse is 0. The force acting is 0. So in that case, what we get is, again, impulse over a certain time is 0. So then we can conclude that the initial momentum is equal to final momentum. Again, that's very useful. It's called the conservation of linear momentum. There are also situations where, because it's a vector equation, the linear momentum equation, so we can also say that sometimes it's only one of the component of this equation that is 0. So it could be that the impulse is 0 in a certain direction. So in that case, let's say then we can only say that the momentum is conserved in a particular direction. I'm moving very quickly. I just want to establish a meeting point. Next we come to two particle systems. So the idea of internal forces. So in work energy theorem, we saw that internal forces do work, and we have to consider that. So let's see if we have a system of two particles and there's an internal force between them. So on particle number 1, it's F12, that is the force on particle 1 by particle 2, and on particle 2 we have F21. And since these are internal forces from Newton's third law, they are equal and opposite. So we are considering, we want to conclude something about the system as a whole, not just one particle. So we start with single particle momentum equation, because that is what we have established, that is what we have developed. So particle number 1, and when we add these two equations, because F12 is minus F21. So when you add them, you get a 0 on the right hand side. So what it says is, if you have a system of two particles, we will generalize it later further when we talk about n particle systems. If you have a system of two particles with only internal forces acting, then the momentum is conserved. Linear momentum is conserved. Any questions? Right. So now we move to angular momentum. We have a fixed coordinate axis x, y, z with a center O, and you have a particle A that has a linear momentum p. We put our phones on silent, please. When the particle A is moving in a line, even then we define a sense of rotation of particle A about a fixed point O. This idea is not very natural, that a particle having a sense of rotation, but it has become natural for us because we have been using this. We define angular momentum of particle A about O as the cross product between the position vector r and the linear momentum p. So note that this is the first physical quantity that involves a cross product in this course. And there is nothing natural about angular momentum and its direction. Make a note there. Important to talk about this because there are some things which are natural to us, like you push a body, there is a force, the force has a magnitude which is proportional to the amount of pushing involved, it has a direction which is in the direction of the push you apply, and you will see in most simple cases the body will move in a direction which is in the direction of push, or at least acceleration will be in the same direction as the direction of push. That is very natural to us. Think about angular momentum, the quantity we have defined. Nothing natural about having an object moving in a straight line having an angular momentum in a direction which is perpendicular to the linear momentum and the position vector. So this is purely for our convenience. We have defined this quantity physically. And again, the direction of this force, it's very intuitive. You apply a push in this direction, the force is in that direction. What about angular momentum? Direction is, in this case, if you think about it, if everything is happening in the zy plane, then angular momentum is in the x direction, outside the plane of paper. But again, that's very non-intuitive. Start using this, then it becomes intuitive with experience. But it's worth mentioning this. This L0 vector is called the angular momentum about a fixed point O. This r cross p, the expression for angular momentum, whenever you have r cross something, it's called the moment of linear momentum. So we'll use these terms interchangeably. Either we call it the moment of linear momentum, that is r cross p, or we say angular momentum. The angular momentum is particularly this quantity r cross p, and moment of anything, any vector, is simply r cross that vector. So we'll talk about moment of force as torque just now. So this was, of course, three-dimensional motion that we had shown. So if we simplify things to 2 dimensions, in this case, it's a planar motion. So linear momentum mv and r are in a plane. So then L comes out to be outside the plane of motion. So L is, in this case, the sense of rotation is counterclockwise. That's the direction of L. Direction is clear, so we'll talk about the magnitudes for this 2D case. Now we can understand this as mv times r perpendicular or we can also understand this as m times v perpendicular times r. Different ways to interpret this. Another way to interpret this is so you split the momentum into its components. So in this 2D case, our linear momentum mv has an x component, we will call mvx, and it has a y component, we will call Vy. So Vx vector is the Vx magnitude times I hat, so it's a vector, I've drawn an arrow, and Vy vector is Vy magnitude times j hat. So we can understand this. So let's say the R vector we have has two components. So one's the y component and the other is the x component. So what's happening is, if you look at MVX by itself has a tendency to provide a clockwise sense of rotation about O. So we can write L direction, again we don't care because it's a planar system, so direction is outside the plane of paper. So this is MVX times y, it has a clockwise, so clockwise is negative, and if you look at MVY, that has a tendency to rotate counterclockwise, and the distance of MVY from the origin is x, distance sorry, from the y axis is x, the perpendicular distance. So this becomes plus MVY times x. Different ways of interpretation, but mathematically that is the same. Overall, the vector becomes that clear? So now we differentiate angular momentum about the point O with respect to time. So we get dr by dt cross p. What is this quantity? What is dr by dt? Velocity. And what is p? M times velocity. So v cross v is 0. And what is dp by dt? Force. So this is the moment of force F about the point O. And this called the torque of force F. You can also say just torque about, well, we have to say about point O. So we denote this as tau O. It's one of the ways to symbolize torque or the moment of force. So just like you had force is equal to the time rate change of linear momentum, we have an analog in rotation sense of rotation that we have defined. The net torque or the torque about point O is the rate of change of linear momentum of the object about point O. Remember this, about point O, don't confuse that. And this was the reason we defined L, because there was nothing natural about L, but this equation is going to be very, very useful. We will see, you have already seen, you have used this equation in the past. Now, I have always been saying that point O is a fixed point. The reason is because if it is a moving point, what you get is there is an extra term that appears. The velocity of point O, and of course, if O is a fixed point, then this VO becomes 0. But if O is moving, then you get VO cross P. Now, I will leave this to you to derive it yourself. This is a good exercise. So, you assume that your point O is moving. Then try to derive the relationship between the torque and the rate of change of linear momentum for that, about that moving point O. When I upload the lecture notes on Moodle, I will include the derivation, but for now I will ask you to do it later yourself. This is one of the most important tools that we have in mechanics when applied to rigid bodies, which is a collection of particles. So, moving similar to what we did, doing similar to what we did in linear momentum. So, if we can define an angular impulse, we will call the angular impulse momentum principle. So, the angular impulse, which is this quantity, when added to the initial angular momentum, gives you the final angular momentum, very similar to what we had in linear momentum. Now, the motions happening in a plane, you do not even need to write the vector form, because we know that the sense of coming out of the plane of paper is positive and going in is negative, and these are the only two directions of angular momentum or torque you will have, because the motion is happening in a plane. So, for motion in a plane, we sometimes write it in a scalar form. So, the direction is understood from there. So, from this we can get the idea of conservation of angular momentum. There are situations where the torque is 0, that gives us the initial angular momentum is equal to the final angular momentum. There are situations where one or more components of torque is 0 or 0. In that case, the angular momentum in those directions is conserved. So, if let us say the x component of torque is 0, that means the torque about the x axis is 0, that says the angular momentum, again we are talking about everything about a point O. Make sure you keep writing that. If you miss it, then you can potentially make a mistake. The angular momentum about point O, x direction initially is equal to angular momentum about point O in the x direction. Fine. For a system of particles, let us say 2 particles in this case, with only internal forces acting, as we saw earlier, you can again write torque equals dl by dt for each particle and then apply Newton's third law. You will see that you get the angular momentum is conserved for the system if only internal forces are acting. Does it matter if the internal forces are conservative or non-conservative for this to be valid? It does not matter. This was a very quick recall of the ideas of linear momentum, angular momentum, and the conservation of linear and angular momentum. Under what situations you can apply those conservation ideas. So we will do a problem now. We will work on a problem. This is an elaborate problem. We might not be able to finish the whole problem, so I will upload the remaining part on YouTube. But let us start discussing the problem. It is the problem of a conical pendulum. So we will discuss the problem in different multiple parts. The first part is you have a conical pendulum. The conical pendulum is a pendulum which has a rod and a mass m. The rotation, angular speed omega with which the rod rotates, and rod is at an angle alpha. The rod is massless. You can assume the rod to be massless. Rotates at constant omega. So you have to find, the first part is find the angle alpha for a given omega and length L of the rod. Now, is the intuition clear that if I rotate, if omega is larger, the angle alpha increases? Let us solve the problem and find out what alpha is for a given omega. You can do it yourself as well. It is not very complicated. You have to choose a coordinate system. So the coordinate system I would want to choose is r theta. So r is, there is a center here, we will call it A. This point we will call B. So one is r hat, which of course will change with time. For this instant it is like this, and theta hat is this, and there is a third direction as well here. So we will call it Z. the bob is moving in a plane. We can see that. That plane we can define r theta, and then z is simply perpendicular to, so it's r cross theta. Let's see what are the forces acting on the bob. One's mg and the other is the tension because of the rod. Now there is no acceleration in the z direction. Z double dot is 0. This tells me that T cos alpha is mg. Now let's look at the r hat direction. So the acceleration in the r hat direction is, if you remember, r double dot minus r omega squared. R double dot is 0. It's rotating in a circle of constant radius. So we are saying that if you fix omega, it will take a fixed alpha. So that means the r will also be fixed. So this term is 0. So we have AR is minus r omega squared. So what that gives us, and there is also a relationship between r and L. L cos L sin alpha is r. If I use 1, 2 and 3, that simply gives me G upon cos alpha that is the equation we get. That equation, the easiest tendency for us is to say that G by cos alpha is omega square L, but it has two solutions. The other one is sin alpha is 0. We have to be careful with that. It says either sin alpha is 0 or cos alpha is G upon omega squared L. When is sin alpha 0? Let's look at the other way around. When does this solution fail? What happens with G when G by omega square L is greater than 1? Is it possible? So this basically means omega is less than square root G by L. So this is the sin alpha equal to 0 is basically the situation. So if you do not give it any omega, it will just sit vertical. It will not have any tendency to fly out. So when omega is less than a certain omega naught, which is square root G by L, it will not be able to fly out. So the alpha is 0. That means just sitting vertical, sitting and rotating as well, because there is an omega. So it's rotating about its own axis. In that case, our r, the radius r is 0. So AR becomes 0. So we say the bob vertical and rotates with omega, which is less than equal to square root G by L. So this is for the first solution, and the other one is for the situation where actually your omega is greater than this. Okay. So this we talk about the failure, which is the left case. So when omega is greater than square root G by L, if it's large enough omega, it will have a tendency to fly out and form an angle with the vertical. Have I made a mistake somewhere? On the left hand side, this one. Then probably this one, right? We're talking about failure. So we were trying to find out under what condition is cos alpha equal to g by omega square L does not work. So cos alpha cannot be greater than 1, right? So we are trying to understand the two solutions. So let's understand the situation now. You take the bob, you rotate it. It's sitting vertical, you rotate it with an omega. If omega is less than square root g by L, then it sits vertical. Now you can still keep it down and rotate it faster. It will keep rotating faster, but if you give it a slight push, then it takes an alpha. Okay? And that slight push will always, if you're physically doing it, you will, I mean, mathematically you can rotate the bob without giving it any motion in the plane. So it will rotate as fast as you want, but that is an unstable solution. It's like you put a ball on the top of a mountain. It can sit there if the slope is 0, but as soon as you give it a push, it will fall down, it will go down. So that's an unstable equilibrium. We'll talk about the idea of stable equilibrium, unstable equilibrium in the sense of potential energy function and so on, once we talk about what these operators gradient, curl and divergence mean. So we will have a dedicated lecture on that, but for now, is the mathematical solution clear here? So this is the first part of the problem, and I think we are out of time now. So I will write the problem, the second part, and I will ask you to try it yourself, and the solution will be available online. So in the second case, you have to find the angular momentum LA and angular momentum LB about the points A and B respectively, and show that torque about these 2 points are individually equal to the rate of change of angular momentum. So tau A is equal to dLA by dt and tau B is equal to dLB by dt. So this will help you understand there are certain smart choices of the point O that help you simplify the problem. And but this equation is valid for all points, and LA need not be equal to LB. Please solve this problem, and this requires use of polar coordinates, so it will help you practice polar coordinates as well. I'll upload the solutions by today evening. Thank you.